Okay, so let's continue. Ah, okay. So we say like from x bar from sampling distribution or x bar follow normal, y bar follow normal, then we have this, right? Okay, so we have this x bar follow normal, then these things follow normal, and this follow standard normal. Okay, so on the HO, we say HO usually is mu1 equal mu2. On the HO, so mu1 minus mu2 equals 0. So we have this x bar minus y bar, x bar minus y bar over this, like sigma 1 square over n1 plus sigma 2 square over n2. So this follows standard normal. Okay. Then if we replace S1, replace sigma 1, sigma 2 by S1, S2, then we say those things, we say roughly follow a T distribution with degree of freedom is that. Okay. So here we say we just say roughly. So we have another question. In which case we can have a precise distribution, not roughly. Okay, so let's check a typical situation, a special case. Okay, so let's say the problem is, we say, where T distribution come from? We say if we replace sigma by S, then Z distribution become T distribution, right? So here is we replace 1 sigma by S, 1 S, then Z will become T. So in special situations, if this 2 sigma, actually we have only 1 sigma. Sigma 1, sigma 2 the same. Sigma 2 equals sigma 1 equals sigma, then there's 1 sigma. Then we can have exact T distribution. Okay? So we can say the problem is if we replace 2 sigma by 2s, we have some trouble. If we just replace 1 sigma by 1s, then Z is T, right? They become T. Okay, so if, let's say, if here sigma 1, sigma 2 is the same, equals sigma, then we can take sigma outside, right? So we have this, like x1, x bar minus y bar over sigma and radical 1 over n1 plus 1 over n2. This follows standard normal, right? So here we just use this, like x bar minus y bar over. So here like sigma square over n1, sigma 2 square, no, sigma square, sigma 2 still sigma, right? N2. So this follow normal, standard normal, right? So this is sigma, we can take it out. Okay, so we have this. So even though we assume sigma 1, sigma 2 the same, equal, then like we still don't know sigma, right? Okay, so we should replace sigma by S. But we have S1, S2. So replace sigma by which S? If we replace sigma by S1, why not S2? If we replace by S2, so why not S1? Okay, so how to replace the sigma This is the question. So we cannot simply replace by S1 or replace by S2. So to solve this problem, we introduce this notation: pooled variance or pooled standard deviation. So what is pooled means? Means put together, right? Like we have variance, we have two variance, like S1 square, right? S2 square. We have the two variance. Then pooled variance, put them together. So we define pooled variance is the weighted average of those two variance. Weighted average of S1 square and S2 square. So what is the weighted average? So before we regard average, just add them up, divide this number, right? But the weighted average is like those numbers use different weight. The importance of those numbers are not the same. So for example, like if we want to find the average of 10 and 20, we say, oh, 10 and 20 is just add them up, divided by 2, right? So for this one, we can rewrite this as like equal half times 10 plus half times 20. Okay. So we can regard this coefficient half is weight. So we weight the same half. So if not the same, for example, like we weighted those 10 by 2 and 20 by 3, so 20 weighted more. Okay, so total weight equal 5, right? So we just use this. The 10 weight is 2 over 5. So I'm sorry, there's a 20. I made a mistake there. 23 over 5. Okay. Okay. So weighted average is a very useful notation, and in many situations we will use weighted average. Okay. So now we can define the pooled variance is weighted average of S1 square is those two variance. So weighted on what? We say weighted on their degree of freedom. Okay, we put this here. Weighted on their degree of freedoms. Okay. So S1's degree of freedom is n minus 1. n1 minus 1, yeah, n minus 1, n1 minus 1. And S2's degree of freedom is n2 minus 1. Okay, so total degree of freedom is n1 minus 1 plus n2 minus 1, right? So here n1 minus 1 plus n2 minus 1. Okay, so we have this formula. We say there's a pooled variance. Okay, so this formula looks complicated, but once we understand, then this formula is easy. We just weight on n1, weighted on their degree of freedom, right? n1 minus 1, n2 minus 1, right? Okay, so the weighted average is really common sense. Let's say, like for example, we have two classes, and class 1 average is 80, class 2 average is 85. So what is the average for all? Like here we say class 1 80, class 2, average 85. So what is the average for these two classes? So we say you cannot simply use their average 80 plus 85 divided by 2. So this is a big mistake, right? Okay. So you cannot do this 80 plus 85 divided by 2. So this is totally long because we need to consider their class size. So if big class, they should weight more, right? So actually the average for all, we say average for two classes should be weighted average for these two numbers, and weighted on what? On their number of students. So if class 1 student 20, class 2 students 30, so they like here 20 multiplied like this, then total weight is 50. So there's total weight 50 is total number of students for these two classes, right? So this is a very simple example and a very typical example. Like average in class 1 is this, average in class 2 is this. So what is the average for these two classes? So we should consider the students' number, right? We should weight it on them. Okay. Okay. So in general, like, if we have three classes, it's same, right? Suppose like class 1, class 2, class 3, average 80, 85, 90. Then what is the average for all? So we should say this average for all is, we have three average 80, 85, 90. Then this averages should be weighted on their number of students, right? Number of students. So this 80 class 1 student 20, and this one student number 25, and this one student is 30, right? Okay, and then divided by total weight, the total number of students for these three classes, right? So let's say this is 75. Yeah, so 75, right? So okay. So find the average for the three classes. We should do this way, right? So this we also can, no, we already know this. Like there's class average for all three classes. We also understand this way. Total students 75, right? So total points from class 1 is 20 multiply 80, right? So this is total points from total scores from class 1. Then says total scores from class 2 plus total scores from class 3, right? Okay. Okay, so now we understand what is the weighted average. Weighted average for so polar variance is weighted average for S1 this S1 squared 2 variance weighted on degree of freedom. Okay. Okay. So now let's consider this problem. Like, let's say we just do the same problem, like compare. We wanted to compare the two classes, or can we say class 1 perform better than class 2? So class 1's average is 84, class 2's average is 81. So we did this problem before, but here we emphasize, we say with the assumption of equal variance. So from here we can say, oh, those two numbers is quite close, or we can assume their values are equal. Okay. So the problem, so we just listed this as testing problem. So HO is same. HO is mu1 mu1 equal mu2, or mu1 mu2 no difference. So HA is mu1 larger than mu2, right? Class 1. I just wanted to show this evidence is strong enough, right? So from this evidence, I wanted to say my class perform better than other class, right? Okay, so the test statistic, so by now is this, like we use this formula, okay? Test statistic, if we assume values equal, so we take we replace sigma by this variance, upward variance, upward standard deviation. We use this formula. Okay, so at first we need to find SP. So SP is standard deviation upward. This P stands for upward. So upward means put together. So at first we need to find the SP. So we find SP square. Calculate the upward variance. So this equal with the two variance, weighted average for these two variance. So here 5, 6 standard deviation. So variance is 5 square, 6 square, right? So this upward variance, we don't need to use the formula. We just use of understanding. So here we have two variance, 5 square, 6 square. So this is weighted average. So weighted on what? On the degree of freedom. So here 5 square, this degree of freedom is 24, right? N minus 1. This degree of freedom is 19, right? So weighted on first degree of freedom. So total weight is 24 plus 19, which is 43, right? Okay. So you got this, right? So easy to, so you can easily find this number. Yeah. So equal 29, 84. Then take a square root. We find we find poor standard deviation is 5.46. Okay. So then we just plug in here 5.46. Okay, so you calculate, we find this this test statistic cutoff point is 1.83. Okay, so now we want to determine this is a big number or small number. So to determine big number or small number, we need a critical value. We say so we need a critical value. So here there's a t critical value, right? Critical value. Okay. We need this. T means we get this number from T table, right? Okay. So for T table, we at the first need to determine degree of freedom. So what is the degree of freedom? So in this case, degree of freedom, we also is in one, just add this 2 degree of freedoms. Okay. Or we just say, so degree of freedom is just this denominator. Now, when we find SP, this denominator. Okay, this denominator is degree of freedom for these variance. Okay, so remember for find samples variance is equals us, like divided by n minus 1. So we say this n minus 1 degree of freedom, right? So use this use this, like xi minus x bar squared. So here with the denominator divided by this denominator is degree of freedom. So here denominator is 43, so 43 degree of freedom. But anyway, like here we just remember, in this case, degree of freedom is just we add this 2 degree of freedom together, n1 minus 1 plus n2 minus 1. Okay, so this is 43. So then we need to check a table, find this. Okay, so let's check a T table. Okay, T table here. So degree of freedom is 43. So we say degree of freedom is 43. But in the T table, we do not have 43. So we just choose close one. So we just choose 40. Okay. This line. Then one tail, two tail. One tail, two tail. Or we say one tail, right? Because let's say one tail, two tail. Actually, we just come to our problem like VH is larger than. We just check one side, right? Like larger than or less than, just one side. So one tail. One tail. So alpha is 0.005. Okay. So we just say so degree of freedom 40. Okay, we just from table we check this, like 40 degree of freedom 40, one tail 0.005. Let's say one tail 0.005. Thus, okay. So let's go down degree freedom of this line here. Go down. Okay. So we find this is our critical value. Okay, the degree of freedom. So we have to choose 40. So let's say this is 1.684. So this is we say critical value, right? So 1.684. So then we use this number to determine 1.684. I put it to here. 1.864. 1.864. Right? 64. 1.6. No. Let me see. This is what 1.684. 1. Oh, I made a mistake. Maybe 1.6, right? Yeah, 1.684. 1.684. Okay, so I'm sorry. This is long. 1.684. Okay, so use this as standard. We can say this number is big, right? This number 1.83 is big. Okay. Okay. So let's say, so go back to here. So we can say 84, 81. So in this case, this difference is significant. And can we say class 1 perform significant better than class 2? So this time we say yes, right? Okay, so we say quite the same problem if we use different assumption, then we can get a different conclusion. Like here, if we assume values the same or equal, then we can have a more precise distribution for this test statistic. Okay. So if this assumption is true, then our conclusion is true. We say I can so class 1 perform better than class 2. So certainly we have this question: how can we know this assumption is true? Like 5 and 6, how can we regard these two numbers quite the same? So this is another story. Logically, we also should check this assumption, right? But this is another story. So here we do not discuss this. We say, so if we assume the variance are equal, same variance, then we should use this formula as for test statistic. So here we have two formulas for test statistic. So don't get confused. That one is this, right? X bar minus y bar. So this is S1 square over N1 plus S2 square over N2. Okay. And for this, the degree of freedom, we just use smaller one, right? Minimum of N1, minimum of, I'm sorry, okay? N1, no? N1 minus 1, N2 minus 1. No. Okay, so in here, degree of freedom is just N1, just add them up. N1 minus 1 plus N2 minus 1. Okay? Okay. So let's check this problem again. So okay, we use the same problem, but this is just for our convenience. Actually, we should use a different example, but the story quite the same. Like we actually suppose that we don't need to care about those things. Okay, we just use a table or class 1 or company A. We have for this sample, we have sample size, sample mean, sample standard deviation. For this sample, we have sample mean, we have sample size, sample mean, and sample standard deviation. So we have just N, X bar, and S. Then we want to compare, like this is bigger than this. Okay, so here we under the assumption of equal values. We want to conduct whether the customer certification level in company A is higher than that in company B. Company B, company 1 company at this level. So all this story quite the same. So HO equal HA is larger than, okay, and the test statistic Z value, T value. So, but anyway, like here we use this formula. So T value, Z value, we just use this formula. Should be T value logically, right? But here, if sample size quite big, then Z value, T value, no much difference. But anyway, like here, test the statistic uses formula, right? T equal x bar minus y bar over so SP so 1 over n1 plus 1 over n2. We use this formula. Okay, so at the first we need to find SP square variance. So we say variance of pooled variance is the weighted average for those variance. So here variance 0.51 square and 0.52 square. So 0.51 square, this variance, and this variance. So weighted average, weighted on what? On the degree of freedom. So this 0.51 is from company A. So the sample size 174, so degree of freedom 173, right? So 173 as weight. And for this 0.52 square, this sample size is 355, so the weight is 354. So this is degree of freedom, right? And then total weight is this 173 plus this, okay? And then after some calculation we find this, and is P equals this. Okay, so then this formula, yeah, we have to use this formula. Okay, so if we use a different formula, I will take a point. Like if we assume variance equal, you have to use this formula. Okay, so x bar minus y bar, so SP, so SP put this this number to here. So 1 over n1, 1 over n2. So here we after some calculation we find this. So we say this number is big. No matter there's t, check a t table or check a z table, this number is big, right? So we can get a conclusion. Their difference is big. Okay, their difference is significant. Okay. 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 So here we say if sample size quite big, then okay, let's say then C table, T table, doesn't matter, right? Okay. Okay, so now actually I need to check one example. Let's say, suppose like let's compare two proportions. We also have the same story. Like if we assume variance the same, then we should use this different formula. Okay, so for proportion, compare, let's say, compare two proportion. Let's check the same problem. Like we say, like we have P1 hat equal like 42, the P2 hat equal 45%, and here we check 1,000 people, and here we check the so n1. Okay, so n2, here we check the 2,000 people. We get his percentage popularity or his percentage is 45. So can we say there's P1 P2 is significantly larger than P1, or this candidate percentage or popularity is significantly higher than that candidate? Okay, so here we say find test statistic. So here we have two formulas. One is use this, right? P1 hat minus P2 hat. Okay. Then with this, right? So S1 square, so S1 square P1 Q1 over N1 plus, so S2 hat, this S2 squared P2 Q2, right? P2 Q2 over N2. So we can use this formula. So this t value, so because the sample size is quite big, so we still use z value, right? Okay, so now let's say if we want to conduct this testing under if we assume variance equal variance equal, then the formula is like this: P1 hat minus P2 hat. So here take the P, we say P hat, so 1 over N1 plus 1 over N2. Oh, I'm sorry. Here's sigma, so there's P hat, Q hat. Okay. So what is P hat? What is Q hat? What is P? So here we say there's P is port. We also have this port port variance or port standard deviation or port percentage or port proportion. Okay. So what is a port proportion? So port proportion is we just put those people together. So totally, we can have this. So P hat is so we put this P hat. So we have totally. So we put simply like this. One. So totally so many people, and then total people like them. So like A, like B, doesn't matter. Like A is this, like B is 900. So this is a port proportion. Okay, and then this PQ, we can regard this is PQ is port variance. Okay. So we can so we can do the same problem. If we assume the variance the same, then we can find the port proportion. Then use this as a formula find z value. Then use z table to find to check this is big or small. Okay. Okay. So maybe we can let's finish this problem. Like so here, let's say this equal. Let me use calculate. Okay, 9 plus 4 to 0 divided by 3. No. Let me see. That is 45. No. Let's see. Okay. Yeah. Okay. So this equal 44. Right. Okay. So we say for like P1 had 42, P2 had for this guy is 45, and put those two guys together, we can say this is the polar proportion of 44. Okay, among 3,000 people, 44% people like them, like this, right? Okay, so then we can find this test statistic. So this equal 42 minus 45, right? The P1 hat minus P2 hat. Then this sigma, this equal PQ. So 44 times 56, right? PQ. But here sigma take square root. Okay, so then okay, so 1 over n1 is 1,000, so plus n2 is 1 over 2,000, right? Okay, so this one is z value. So here just a little bit of calculation. Once we find this z value, so I prefer use Excel, but here I cannot show you how to use Excel. So, but anyway, like we understand those notation. Find this z value, then check z table. We can determine this big number or small number. Okay. Okay. So we can stop here. So today's topic is two sample problems. Two sample problem. So here we just use this formula. Test statistic. Test statistic use let's say use this. This is test statistic. X bar minus y bar over S1 square over n1 is 2 square over n2. Okay, and the typical situation is if S1 is 2 same or value same, so we use this, right? We can take this y, take sigma outside, so this become SP. Okay, so we can take this S squared outside, just okay, so then this is 1 over n1 plus 1 over n2, right? So for t value, we have two formulas. Okay, so it's t. Okay, so don't forget so which formula to use. And if you use this formula, degree freedom is different. Degree freedom and this degree freedom. Okay. Okay. So we here an important notation is weighted average. How can we find SP? How can we find a weighted? How can we find pooled variance? So we have pooled variance, pooled standard deviation. So for 1-0 data, we have a pooled proportion, right? So you understand this notation. So polar proportion is just put these two people together, right? We just find how many people like this guy. Okay. Okay. So okay. So we find this two sample testing is easy, right? The only thing is you should know. Don't get confused. You should use the correct formula for those test statistics. So once we have the test statistic, we need to know, we need to determine those numbers, those test statistic is big or small, right? Okay. Uh, okay, so we can stop here. And so I think by now you you will know you will know more and more about statistics, and you will find statistics that easy and easy, right? Because the process quite the same. We have some evidence, or we have evidence there's a test statistic. Then we need to determine this is significant, significance, or we just check this number is a big number or small number, right? Okay, so today's topic is two samples. So we have one sample, then we have two sample problem. Then next class we will check many sample, like three sample problem or four sample problem, many sample problems. Okay, so those are typical problems in statistics. Okay, okay, so we can stop here. Thank you for watching. Thank you. Okay, bye bye.